Hi, this is Blatnum, and we're going to be talking about game theory. And we're going to do our second example today. So today is going to be an Atlas Reactor specific example. We're going to talk about dashing in Atlas Reactor. So here's how I'm going to set this up. I mean, there are lots of different scenarios where you could find yourself wanting to dash. So I'm going to say that you've got Lockwood, Gray, and Gray is low HP. So if she gets shot, she's gonna die. And Gray's drone is over here. So I don't quite know how to draw Rio. So let's try this. This is a surprisingly good Rio, I think. I hope I don't have to re-record this because it's not gonna get much better than this. And you've got Rio's landing zone. So this is, Lockwood's gonna shoot Gray unless Gray dashes. And both of these are options. I mean, Gray could choose not to dash, and Lockwood could choose not to shoot. So here's how I'm going to set this up. I'm going to say if Lockwood shoots, Gray dashes, I'm going to give this a payoff of 0 from the perspective of Gray. So I'm going to say this is an even trade. This is, kind of crappy for Gray because, she used her dash. She might be in trouble in the future, but I mean, this is what I'm going to, like we said a while ago, payoffs can be finely rescaled without changing your equilibrium strategies. So what value we give this doesn't matter too much. So if Lockwood shoots, but Gray stays, so I'm going to write this little hook thing and then dash. So this hook thing is a negation marker, so this means doesn't dash. I'm going to give this a payoff of -5 because you die, and that's really bad. If Lockwood doesn't shoot and Gray dashes, I'm going to give this a payoff of -1 because not only did you use your dash, so it can't be better than this, but Lockwood presumably did something a little bit more productive than shooting at air. So it's going to be a little bit better. And if Lockwood doesn't shoot and Gray doesn't dash, I'm going to give this a payoff of +1 because, you tricked him, haha, right? Lockwood would have preferred to shoot you, but he didn't. So you got to shoot back at Lockwood and do something productive. And Lockwood, I mean, he missed his chance to kill you. So again, these payoffs are sort of arbitrary. It's just my guess on roughly what the value of these things are, and they're debatable. I talked a lot in the payoff video, in the evaluation function video, about how these can be difficult to come up with, and this is an example where it's very hard to say, oh yeah, probability of winning the game if Lockwood shoots and Gray doesn't dash. That's a hard probability to evaluate. So I'm just making a guess here, and I'm finally rescaling them in this way. So if you want to draw a payoff matrix, it looks like this. So Gray has two options, dash and don't dash, and Lockwood has two options, shoot and don't shoot. So this is a payoff of 0, this is a payoff of -5, this is a payoff of -1, and this is a payoff of +1. So this is our payoff matrix. So now the question is, at equilibrium, how much should either player do each thing? So let's start with calculating how often you should dash. So to calculate how often you should dash, you want to look at Lockwood's perspective. So EV, Lockwood shoots. and you want to get an expression for this, and you want to calculate EV of Lockwood doesn't shoot, and you get an expression for this, and then what you do is you use the indifference principle. You say, indifference principle says EV of Lockwood shoots is the same as EV of Lockwood doesn't shoot at equilibrium. And then the idea is that this side is going to depend on your probability of dashing. And this equation will let you solve for that probability. So let's say, so looking at this, we can say, suppose Gray dashes with probability P. So, all right, what's your payoff? So if you shoot and Gray dashes, then your payoff, then the payoff the payoff from Gray's perspective is 0, right? So it's 0 times P. And then if you don't dash, well, you get -5 times 1 minus P. And then for not shooting, what happens? Well, if you don't shoot, you get -1 times P, and then +1 times 1 minus P. And so let's equate these two things and see what we get. So the first line is -5 times 1 minus P, and the second line is -P plus 1 minus P. So let's clean these up a little bit. Here we have -5 plus 5P equals 1 minus 2P. And so this gives us 6 equals 7P, and so P is 6/7. So that's our, that's how often Gray should dash, right? We said Gray dashes with probability P. So Gray should dash most of the time. I think this is a pretty familiar result, that you should dash most of the time. Most people will dash if they're about to die. So this shouldn't come as any surprise, I think. All right, now let's figure out Lockwood's thing, how often Lockwood should shoot. So suppose Lockwood shoots with probability Q. Well, all right, EV of Gray dashing is something. EV of Gray not dashing is something else. So let's look at this and figure out what happens. So when Gray dashes, if Lockwood shoots, the payoff is 0, and if Lockwood doesn't shoot, the payoff is -1. So Lockwood shoots with probability Q, so it's 0 times Q minus 1 times 1 minus Q. And then if Gray doesn't dash, well, she gets -5Q plus 1 minus Q. So again, we use the indifference principle to equate these two things. So you get -1 minus Q is equal to -5Q plus 1 minus Q. And now let's solve for Q. So this is Q minus 1 equals 1 minus 6Q. So let's move this 6Q over. We have 7Q equals 2. Oh ho! So Q equals 2/7. So this might be a little bit more surprising than the last one, because I think that common wisdom, right, this is the probability with which Lockwood shoots. So I think common wisdom is if you can kill someone, even if they've got dash up, everyone should always at least check the dash. And this suggests that at equilibrium, that's not true. That most of the time Lockwood should not shoot at a Gray who's almost certainly going to dash. Like they shouldn't waste his turn. And if you think that maybe this is an artifact of me having chosen the number that I chose, I encourage you to go back and change the payoffs and try it yourself, or you could even have payoffs be variables and try it that way and see what you get. But I think fairly consistently what you're going to see is that Lockwood shouldn't shoot at gray that often at equilibrium. So again, this is at equilibrium. So so the question then we might ask is well, so why do people in Atlas Reactor not do this? Why don't they play the equilibrium strategy in this situation? And I think the answer is because they're maximally exploiting a population tendency. You see, people are supposed to dash 6/7 of the time in the situation as gray, and they don't. I think they dash a little bit less than 6/7 of the time, and so the maximally exploitative response is to always shoot at where they're going to be, right? Because even if they dash like 5/7 of the time instead of 6/7 of the time, you should always shoot them. That's how you maximize your EV. So because some people just like, for whatever reason, they're going to miss it. They're going to miss that they're in danger. They're not going to see Lockwood. They're just a new player. They don't understand how to count. I don't know. But for whatever reason, people don't dash in this situation. And so it's a maximally exploitative response against a population tendency to always cover the no dash option. So just shoot 100% of the time. So it certainly would be a mistake to say that people who always cover no dash are wrong, but I think it's very important to be aware of why you're doing it, that you're exploiting a population tendency, and you have to be aware sometimes of when you're in a situation where that population tendency, is no longer applicable, right? Maybe, you're against very strong players who aren't going to miss it and who are always going to dash. Then you should maybe consider adjusting your play. Because of course, the exploitative response to always shoot is always dash. And you'll see this with good players as well, that they'll always dash. But no one is good enough to stop shooting. This might also be a little bit psychological. Because if you don't shoot and they don't dash, you feel really dumb. At least I would feel really dumb. And it's hard to accept that that's just variance. So I think that people also on a psychological level just prefer to always shoot, and they really don't want to miss out on a big payoff, even if on average it's a bad thing to do. So I think that these are the population tendencies you'll see in Atlas Reactor, and of course the way to exploit it is to always dash and to never shoot. If you're against the right people. So there's one thing I did that I didn't justify in all of this, which is I applied the indifference principle. If you recall the indifference principle, indifference principle says you're indifferent between the pure strategies that you play. So there's one thing that we need to check if we really want to dot all our I's and cross all our T's. And that is to check that we actually do play, that at equilibrium, you both shoot and don't shoot, and dash and don't dash. So let's look at it this way. This is how you do this. So suppose Lockwood shoots all the time. Could this possibly be an equilibrium strategy, to always shoot? And, well, what's Gray going to do if she wants to maximally exploit always shoot? Well, she's going to always dash. That's the unique, in this case, maximally exploitative strategy, because against always shoot, the EV of not dashing is just lower than the EV of dashing. So the unique maximally exploitative strategy against always shoot is always dash. So Gray is always dashing if Lockwood is always shooting. Now, if Gray is always dashing, is Lockwood maximally exploiting Gray? And the answer, of course, is no. If Gray is always dashing, then Lockwood would rather not shoot and pick up a -1 instead of 1. Because remember, these payoff instead of 0. Because remember, these payoffs are from Gray's point of view. So a negative number is better for Lockwood. So what that means is that if you start off with the assumption that Lockwood is always shooting, then Gray's maximally exploitative response is unique, and Lockwood isn't maximally exploiting that maximally exploitative response. So you're not at equilibrium. And you do the same thing for the other three strategies, and you'll see that there's no one pure strategy in that's going to be an equilibrium strategy in this case. So that's what you want to do if you want to justify the fact that you can actually apply the equilibrium strategy. Usually almost every equilibrium is mixed in Atlas Reactor. I mean, it's very, very rare to not have a mixed equilibrium, just because there's always something your opponent can do that will, they'll make you regret what you did. Like, if you could see your opponent's actions before you chose your own, then, I mean, you would go around in circles, right? You would very rarely do one thing all the time. I mean, it happens, but it's quite uncommon. So all the interesting situations, that doesn't really come up. So if you don't want to check and just assume that your equilibrium is mixed, I mean, that's probably safe. But if you want to be, if you really want to be meticulous about things, then you should check. All right, so that's dashing in Atlas Reactor. And that's how you would analyze that situation, and that's the conclusion you would come to. And, hopefully in game this is actually practically useful, because you can see these kinds of situations or similar situations come up, and you can make decisions based on what side of equilibrium you think your opponent's on.